Hello, good day everyone. Today's we try to go through some of the most important things in mechanics, which is vibration and waves. So before, let me introduce myself. My name is djeffal Salman from the National School of Polytechnic, as you can see here, of Constantine. Actually, I belong to the Department of Mechanical Engineering. Today I will be discussing something about generality on vibration, which is the first chapter of my course, which is about vibration. So we will provide with a comprehensive overview of the fundamentals concepts in this area. So let's jump to the table of content, as you can see here. Here what we will cover in today's presentation. We start by an introduction, then definition of oscillation, and so forth, until we finish with the Lagrange equation. And of course, we will try to draw a conclusion about this chapter. So let's start with the introduction. What does it mean, vibration? So if we try to define vibration, we can say that it's the periodic motion of a particle or body around the position of equilibrium. This periodicity is a regular and repetitive pattern, much like the rhythmic beating of a heart which circulates blood through our body. Let's provide you with a video in order to understand what I'm talking about. As you can see here, how the particles vibrate just because of that given sound. As you can see here, the particles generates a kind of vibration. Just a brief video in order to understand what does it mean, vibration. So now let's define the oscillation. What does it mean, oscillation? So oscillation refers to a repetitive back and forth movement around an equilibrium position. Common example, it's like the mass spring and electrical circuits with an indicator and capacitor. Here you are just also another video in order to understand what I'm talking about. As you can see here, we have here mass and spring. They oscillates. You can see here that it generates a sinusoidal like motion, as you can see here. So this is what we call spring mass. Just a brief video. So now let's jump to the sinusoidal motion, as I showed you before in the previous video. So we can define it as or we can define it by the function gt equals to a sinus omega t plus phi, where a is the amplitude, omega is angular frequency, phi is the phase, and so forth. So as you can see here, also the different parameters included in this equation. So now let's talk about the Fourier series. So Fourier series actually is like the periodic quantity can be expressed as the sum of sine and cosine function, known as the Fourier series. This enables us to break down the complex periodic function. For example, if we have like a variety or a set of periodic functions, we can break that down into a set of functions, which means into a simpler component for analysis. As you can see here are the mathematical equation of Fourier series, also the different coefficient a0, an, and bn. So now the one of the most important things in vibration is the generalized coordinates. Actually, the generalized coordinates are variables that describe the state of any physical system. For instance, in a pendulum, using the angles. For example, as you can see here through this picture, we can say that the generalized coordinates are theta1 and theta2. One of theta1 for the first pendulum, theta2 for the second pendulum, which means we have two generalized coordinates. This is why I said that that the generalized coordinates are variables that describe the state of a physical system. So and now let's talk about the Lagrange equation, which is actually also one of the most important things in vibration. We can say that Lagrange equation, or equation of motion, which is the difference between the kinetic energy and the potential energy, is fundamental in deriving the equations of motion for a system. The Lagrange equation is given, as you can see here, by the following formula. As you can see here, in our case, we can say that the generalized coordinates here are q dot can be defined, for example, for a two-pole theorem as theta1 and theta2, which means we will have here two equations. Once we solve them, we can understand the behavior of our system. So now let's talk about the conservative system. So the conservative system is characterized by force that conserve mechanical energy, such as gravity, spring forces. The work done by these forces is independent of the path taken, of course. So we can say also that for the Lagrange equation, we can also have that added, or the additional terms here, which is the dissipation. Once we have the dissipation, we have to add this, we have to modify the Lagrange equation. We can say that the frictional force, which is can be represented by the following term here are. So frictional forces dependent on velocity or dynamic friction oppose motion with and vary with speed. So which means when damping is present, it modifies Lagrange equation by adding this term, which is the dissipation, as you can see here, different to the previous equation, which means we do not have this term here. So also let's talk about the time-dependent external force. The time-dependent external force, which is refers to an external influence. The external influence acting on the system whose magnitude or direction, if you can say, changes with time, which means also the Lagrange equation is modified once again. We have here, instead of zero, we have a force. This is the time-dependent external force. You can see that Lagrange equation is one of the most important things to understand any kind of system. So finally, in this chapter, we have provided with an overview about vibration, defining oscillation. We have also said that Fourier series can help us to break down a set of complex functions. We have also understand what does it mean generalized forces, generalized coordinates by describing that the coupled pendulum. Lagrange equation also to understand or to grasp the behavior of any kind of system, and so forth. You can see through this course we have managed to understand a bit about vibration. So I would like to thank you so much for your time and watching. Thanks. That's it. That's all.